Okay, on Moodle, these videos are up there already from last week, so if you want to start, like if you missed class, you might want to go there and watch the video associated with the week and day. We are in week 2, day 1. We'll see how far we're going to get with this. Now, a lot of what I'm going to go over is stuff you already know, but I want to give it a spin so that the confusion that I know is there hopefully goes away. And the reason that this gets kind of confusing is it deals with proportions, and proportions lead to percents, and people do not treat percents the correct way most of the time. They understand a little bit about them, but every time I ask anything about percents in any class I teach, and I'm talking up to Calc 1, they don't know what I'm talking about. So I want to be really clear about what's what as we go through this whole thing. There's stuff you've seen before, it's just I feel that either your memories are bad, you were taught really bad, or you kind of just wung it.
We got older.
Or some of us got really old.
That's right.
Yeah, it's a bunch of old.
We're not old. Old is good.
Depends on your point of view, I guess. Personally, I'd rather be young. I'd rather be young.
Old is good when you're still good.
So let's start off with something we recognize. Caloric. Certain medicine. Abbreviation. George weighs 205 pounds. A certain medicine is administered at 2 milliliters per 5 kilograms per day. How much should he get per day? Per day. If anything, you should have one thing memorized. George weighs pounds, and this medicine is administered as kilograms. So you should already know how many pounds are in a kilogram. Memorize. 2.2. That one you might want to just keep in your head. 2.2 pounds equals 1 kilogram. Okay. Now, we'll do this the old-fashioned way, the way I showed you last time, but then by the end of this first session, you should be able to do it a different way. So then it gives you 2 different possibilities. All right, so where should we start here? Change the weight into kilograms. By the way, kilograms is not a weight, right? Does anybody know what it is? Weight is measured by gravity. Like, you weigh a certain amount here, but if you go to the moon, you weigh less. 1/6 less, that's a great diet right there, just going to the moon. But kilograms is mass. Mass doesn't change no matter where you are. All right, so that's why we want to change it to kilograms. So you start off with 205 pounds. Then what?
You divide by 2.2.
Over 1.
Put it over 1. You multiply by
1
over 2.2 what?
kg. I mean pounds.
Pounds on the bottom, kilograms in the top. I highly suggest you don't worry about the numbers, worry about the measurements first, how their units are. All right, so the operation here is division. The pounds go away. So what's 205 divided by 2.2?
93.18.
93.18. So 2 kilograms. So now we know how much the patient weighs. Now, whether you do it my new way or the old way, you still have to change the patient into kilograms. All right, the old way for 2 milliliters per 5 kilograms. Well, what do I have? Well, I have 93.2 kilograms, since it's an individual number over 1. And I want to multiply that by something that has kilograms in the bottom. So it goes away.
But is we doing the same thing, it's just a different way?
The same way right now. I'll show you the different way in a little bit. So what goes on the top?
Milliliters.
Milliliters, and there'll be 2 of them for every 5 kilograms. So the kilograms will go away, and you go to 93.2 times 2 divided by 5. Just do it all in one fell swoop. A lot of you are doing sub-calculations,
37.
and you really don't want to do that. You want to just type it all into your calculator and get an answer. One of the most missed questions on work for week 1 was changing the years into seconds. A lot of you did sub-calculations and were rounding your answer. And once you start rounding your answer at the end is going to be automatically wrong. If you typed all the calculation into your calculator and just hit enter, you would have gotten the right answer. But a lot of people subbed it all the way through. What's this equal to?
37.28
37.3 what?
28.
milliliters.
37. Are you rounding?
I'm rounding it nearest 10 milliliters, right? So that's one way of going about it, using unit conversions all the way through. So what's the other method? Well, it starts with this idea, proportions. What are proportions? Anybody know?
Part of a whole.
Oh.
Well, that's part of it.
Part of a whole number.
Nah, that would be something else, though. I mean, it's not just part of a whole.
Percents.
Percents lead into it. There's 2 ways of thinking about percents. One of them is proportions. No one knows what a proportion is.
It's part of something.
If you open up a map, of North Carolina and you look at it, to travel from Rocky Mount to Raleigh is probably about 2 inches. Is that how far Raleigh is from us?
Is it
No.
right?
It's
On
more,
the
right?
map.
It's like
Right and
inches per mile, right? It does a little conversion. So to do proportions, it's literally 2 fractions that are equal to each other. One fraction is equal to another fraction. And if you know anything about fractions, 2/4 is the same thing as
1/2.
1/2. So these proportions take advantage of that. Another way of looking at a proportion is their cross product. You know that famous thing called cross multiplication that everybody screws up? You know, they use it when they really shouldn't. This is the case where you use it and you don't use it anywhere else. So both of these are considered proportions. But the more common one, of course, is the fraction equal to a fraction. But if you ever see a product equal to a product, it's also a proportion, but it also could be something a little stranger, what's known as an inverse proportion. And we'll talk about that later. All right, so for example, on a map, 5 centimeters equals 86 miles. You have to travel 27 centimeters on the map. How far in reality? In other words, if you're really going to make the trip from point A to point B, how far are you really going? So to set this up as a proportion, the only thing to remember is you want to keep common things over common things. In other words, we have 2 measurements here, centimeters and miles. And I don't care which one you put on the top. It could be the miles on the top, it could be the centimeters on the top. But whatever you choose, that has to go for the second fraction also. So you're going to choose an order. I'm going to do centimeters per mile as my fraction setup. So the nice thing is, usually when you deal with different units, you have to convert one into the other. Proportions ignore this completely. So it really just becomes a fraction equal to a fraction. So the first fraction I would set up is 5 centimeters over 8 miles. But I'm not putting the units next to them now, because proportions are a little weird. Oh, 86. I lost it. 86. 86. All right, and you're going to set this equal to, now remember, centimeters has to go in the top and miles goes in the bottom. I have 27 centimeters, top or bottom?
The bottom.
Why you say you don't stop?
Top. Centimeters are in the top. So you get 27 centimeters there. What goes in the bottom?
Okay.
First one.
X. Why not?
So it's wrong if you put the males beside it.
What do you mean beside it?
I find it.
20, what the centimeters, 27 centimeters.
27 centimeters. You want to keep your fractions always centimeters over miles, no matter what happens.
No, I'm saying is it wrong just to write it because I'm used to writing it beside it. Oh, I'm saying like in your parentheses.
She's saying like 5 centimeters over 86 miles.
You just
Right,
gotta
the
keep it in
centimeters
the
or
parentheses.
miles.
No, don't write the measurements.
Oh.
Because in proportions, they get a little weird, especially when you cross multiply. This is 86 miles, right?
Oh.
This is 27 centimeters. If you multiply it, then you get a mile centimeter.
Yeah.
Oh, okay.
And it just gets a little weird. So proportions are probably the only place where you kind of drop things. All right, how do I solve this?
5 times 27.
No.
Oh.
5 times
Cross multiply. 5 times x and 86 times 27. So cross multiply. Top of one fraction times the bottom of the other fraction. This only works if the fractions are equal. It does not work if it's plus or times or anything else. It only works if it's equal. What's 86 times 27?
23, 22.
23, 22. And then to solve for x,
Divided by 5.
divide both sides by the number that's next to the variable. So you get x is equal to
464.4.
4.
64.4.
Oh.
Yeah.
Now, to find the measurement for x,
And
Yeah.
then the other door, oh.
and I yelled at you. Wow. The way you have to find the measurement now is to go back to the fraction. The position of x was in the bottom, right? And the measurement in the bottom is miles. So this would be
Miles.
So with this case where you lose the units, you have to be really careful to know where x is positioned so you can bring back all the units. So this trip would take 464 miles. And on a map, it's only a lousy 27 centimeters. Thank God for Google Maps, right? It does all the conversions for you, tells you how far on each road you go. It's kind of boring.
How would you know when you use like,
What's that?
how would you know when you use a proportion?
It depends on, like, the problem that I first started off with. We could do that with a proportion. It really depends on how you want to deal with things. Now, proportions are really good for maps, models, anything that's been scaled to size. Those are, I lean towards proportions. But you could use it in a lot of different places.
Okay.
It all depends on what your brain thinks of first sometimes. So let's go back to my first problem. I won't write out the whole thing. How much did George weigh in kilograms?
93.2.
93.2 kilograms he weighed.
Yeah.
The medicine was 2 milliliters per
5 kilograms.
5 kilograms per day, right?
Yes.
Now I can set this up as a proportion, and the answer should come out exactly the same. So let's set it up as milliliters over kilograms. So the first fraction would be 2 milliliters over 5 kilograms is equal to. Now here I'm not going to multiply by a conversion fraction, I'm just going to set it up as a proportion. So for every 2 milliliters, the person's supposed to weigh 5 kilograms. So over here, do I know how many milliliters George is supposed to get? No, put an X there. Do I know how much George weighs in kilograms? Yeah, 93.2. Because I chose the order milliliters over kilograms. Cross multiply. I always try to take care of the variable first so it ends up on the left-hand side. It's just a habit of mine. So x times 5 is?
5x.
5x is equal to 2 times 93.2. 186.4.
Yeah.
Alright, and then to solve for x, you just divide both sides by 5. And what's our answer?
37.28 again. You're gonna round it off to 37.3.
3. Now where x is positioned in our fraction tells you what its measurement is. It's in the top. In the top is milliliters. Is that the exact same answer as the first time around?
Yes.
So there's two different ways of doing it. You can do a unit conversion, try to get rid of your measurement, or you can set up a proportion.
I
Most
like the
people lean
proportions
towards.
better.
The problem with proportion is you can only do it to one-step processes. In other words, if I'm changing years into seconds, this is useless. Does that make sense? So it only works on one-step processes. If you're changing one measurement into another, and that's it. And it generally only works in the medicine field. I don't think it would change, converting dollars into. Well, actually, it probably would work for converting dollars into euros and stuff like that, because it's just a one-step process. But once it goes over one step, this is absolutely
Useless.
I wouldn't say useless, but very difficult to work with. Because then you'd have to set up one proportion to get another one, then set up another proportion to get another one, and it
Well,
kind
for
of just.
that work, I'll do it that way.
You'll do it that way.
Yeah.
Now, I don't care which way you do it, but I highly suggest you do the conversion fractions. It's much easier to see how your measurements are going to pop out the right way. This doesn't even keep order of your measurements right, your units right. Did that? Okay. How about this one? Direct. Oh, by the way, these are called direct proportions, and the reason they're called direct proportions is as one measurement goes up, so does the other. So if your weight goes up, the amount of medicine you get goes up also. This is another example of direct. Kind of a simplistic one. People have in their mind the faster you go, the farther you can get in the same amount of time, which is basically true. The faster you go, the farther you can travel in the same amount of time. A lot of people also have in their brains that the faster you go, you save more time, right? Yeah, we're going to break that fact real quick in about a few minutes. So here we have, you can drive 100 miles in 2.5 hours. How far can you drive in 0.75 hours? Now there's like 3 different ways of solving this. You can do pure algebra, but it takes a 2-step process to get to your answer. Or you can do proportions, and that actually works out fairly well. So what are my measurements that I want to concentrate on? Hours and miles. Which one do you want to put on the top? Miles is more natural because you're used to miles per hour rather than hours per mile. So we'll put miles in the top and hours in the bottom. Highly suggest you at least write what you're doing off to the side. It's not part of the work, but it does get you to how your measurement or your answer is going to be measured. All right, so what do I put in the top for miles for the first fraction?
100.
100. What do I put in the bottom?
2.5.
2.5. And it's equal to,
X at the bottom.
I don't know how many miles for the second part of the trip, so x over,
0.75.
because hours goes in the bottom, and this is 2.5 hours and 0.75 hours, and miles stay in the top. What product would I do first? Not what you.
2.58.
I would multiply the x times the 2.5 first, just to keep the variable on the right-hand side. What?
I'll let her voice. Keep going.
What's 0.75 times 100?
75.
75. And then divide both sides by?
2.5.
2.5. Don't ever divide by the variable. Why should you never divide by a variable? Why would you never, or should you never divide by a variable?
Because the
The S
variable
gonna
will
end
be
up still having a variable.
What does the variable represent?
unknown number.
Oh, well, I don't
Any number.
Any.
What number can it not be if you're dividing?
0.
0. So what's 75 divided by 2.5?
30.
So this is 30,
Miles.
and since x is in the top, it's measured in miles. So you can do things like that. It's kind of neat.
It's fine.
It's break time.
That's easy.
Generally not much harder than direct proportions, but a little bit harder to understand what's going on. Remember, direct proportions, as one measurement gets bigger, so does the other. Inverse or indirect proportions, as one gets big, the other one goes down. Or as the other one goes down, the other one gets big. So they're always vice versa of each other. Do you know of any measurements that do that? As one goes up, the other goes down?
Medicine.
Hmm?
Medicine.
Medicine? Usually if you increase your medicine, there's what would go down?
Oh, I know.
Dosage.
Wait,
The
The
dosage.
solution.
If you add more water, the solution goes down. Okay, that's a good one. Concentration. Any other?
when you take medicine for feeling better.
What?
Well,
I couldn't hear
the
you.
more medicine you take, the less your fever or whatever you
The
had.
fever goes down.
Oh, the time it takes. The more rest you do, the fever goes the opposite direction. I guess you could think of it that way. I gave you an example earlier. The faster you drive, the more time you
Take.
save.
Save.
I hope. If you're late to work, what's your first instinct?
Speed
Get in that car and go as fast as you can.
Get a ticket.
And get a ticket and slow it right down. And instead of being 10 minutes late for work, you are now half hour.
Yes.
All right, so the setup
Move
of
on by me.
inverse or indirect proportion as a fraction is very difficult because a lot of people get confused where things go. So it's much easier to set it up in a single line calculation. All right, so one formula we can look at is this. Rate and time, basically. And if you know anything about rate times time, distance equals rate times time is the formula. The faster you go over a period of time, the farther you go. So 50 miles per hour times 2 hours, you have driven 100 miles. All right. Now, the difference between this is usually if we set this up as a direct proportion, it would be rate 1 over time 1 equals rate 2 over time 2. So instead of having division, it changes into multiplication. But it's still a proportion because I can change it into a fraction equal to a fraction. It's just most people would look at it and it would just be kind of confusing. All right, so if you're driving at 55 miles per hour, I'll put the MPH down below. And you do it, you know, you're driving to work, you normally do 55 miles per hour. How long does it take you?
An hour.
Nah, keep it in minutes. I want to do something
7
really.
minutes.
How long? 7.
What was the question?
7 minutes. Let's do about 20. 20. I'm just making something up. So let's say you drive at 55 miles per hour and it takes you 20 minutes to get someplace. This, if you multiply it together correctly, by the way, you'd have to change minutes into hours because it's miles per hour. But in this case, you don't have to, which is really kind of cool. So you get miles per hour, and this is how long it takes you. So basically, if you multiply these two together, it gives you a distance. So this times this gives you a physical distance, a certain number of miles. Precisely 55/3 of a mile, whatever the heck that turns out to be. And let's say on a return trip, you decided to do 75 miles per hour. And you want to know how long does it take you. And again, you're doing rate times time, which is also distance. And this equal sign is saying that the distance that you traveled on the left-hand side is exactly the same as the distance you traveled on the right-hand side. So it forces them to be equal. And then you can solve for time too. Now the cool thing is this. This is 20 minutes, and it really should be in hours. But after all is said and done, minutes on the left and minutes on the right, if I divide by one or the other, the minutes goes away. So the time frame really doesn't matter. So if it's 55 times 20 minutes or 55 times 1/3 of an hour, the answer is still going to spit out exactly the same, which is really cool because we don't have to do any conversions. All right, let's solve for T2. What's 55 times 20?
1100.
1100, whatever it is. 75 times T2, or T if you wanted, you know. You only need a variable there, or x, but I like t. T reminds me that this answer is going to be in time, rather than just x, and then I'd have to go find out what the variable measurement is. How do I solve for t2?
Divide by 75.
So you divide both sides by 75, and you get t2 is equal to
14.67.
67.
6.
Oh, blah 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 blah. 2/3. 2/3. 14.67 what?
T.
Miles per hour. I mean, minutes.
Minutes. So by driving 20 miles per hour faster, we went from 55 to 75, we saved how much time? No, we did not save 14.67 minutes.
5 minutes, 5, 6 minutes.
About 5 minutes. About 5 minutes.
Yeah.
Maybe 6. No, about 5, because this is really close to 15 minutes.
Let me see.
55.
55.
That's about 15 minutes.
Mhm.
And it only took us 20 minutes at 55, and it's taken me about 15 minutes at 75, so it saved me a lousy
5 point.
5 1/3
And
minutes.
just think about the gas you save if you just drive at 55.
Hey, by the way, what's 1/3 of a minute? How many seconds?
60.
20.
20.
20. It's 60 seconds divided by 3, which is 20. So you save 5 minutes by doing 70 or 20 miles per hour faster.
Okay.
So let's say you're 10 minutes late to work and you normally drive at 55 miles per hour, and now all of a sudden you're driving at 75. Are you going to get to work on time?
No, you got like 85.
You think it's 85? Let's find out.
Wait.
So, example. You are 10 minutes late for work by the time you get to your car and get it started. Now, this makes an assumption. This is an average speed that you're driving to work. You can't drive 70 miles per hour all the way to work, because to get to the highway, you're not going to be doing 70. At least I hope you
It's
don't.
95 now. You have to check. It's saying 10 minutes. Then we can get there on time.
You are 10 minutes late for work. Normally, you drive at 55 miles per hour on average. And get there in 20 minutes. How fast to get there? Oops. How much time do I have to get there? 10 minutes. I'm 10 minutes late. I have to be there in 10 minutes. How fast to get there in 10 minutes? How fast? 110 miles per hour. If you do the setup, it would be rate 1, T1, R2, T2. The rate for the first part of the trip is 55 miles per hour. The time for the first part of the trip is 20 minutes. The rate for the second one, I don't know, so I'll just leave it as R or R2. It really doesn't matter. The time that I'm going to have to get there is 10. So half the time means you have to double your speed. So this is 1,100, right? It is equal to 10R, and divide both sides by 10 for the algebra.
Why you say you double it? You added it already. We do it again.
Well, I'm going through the algebra here, but technically if you have to double or half your time, you have to double your speed.
Oh.
So this would be 110 miles per hour. So if you're 10 minutes late for work, is there any point in speeding?
No.
Absolutely not. Because to get there on time, I don't think many people's cars do 110 miles per hour. And I'm quite sure you kill yourself or somebody else.
Might be
Or
one
you definitely are going to get pulled over. You'd be flying by cars doing 110 miles per hour. You'd be like,
You just gotta let the state trooper know you're working on a perfect attendance bonus.
yeah, my wife is pregnant, she's going to labor, I gotta drive this fast. Yeah,
Yeah,
that's not
that's
gonna work. So if you're late for work, guess what?
You're gonna be late.
You're gonna be late. So no point even driving faster than you normally drive, just
I'd be like,
drive.
oh well.
Just drive.
If you try to explain this to somebody that
You cannot explain this to somebody. They think in the back of their heads that they can drive faster and get there on time. But it's an inverse proportion, so it's not exactly. A lot of people think of it as a direct proportion. The faster you go, the farther you drive, which is true for a certain period of time. But if you're trying to do the reverse of it, it's an inverse. And what happens is you save less and less time as you go faster and faster. Which is kind of cool. You want me to explain that part? Fine. Another thing we can do with inverse proportions. Oh, cool.
It's got fans.
She's diseased. No.
Damn.
A lot of people, if you work with anything like diluting medicine, chemists, I bet you could probably do money too with this. I haven't tried. So let's talk about you add 1 cup of sugar to 2 quarts of water. Why would I add 1 cup of sugar to 2 quarts of water? Kool-Aid. So I'm going to make Kool-Aid. Now, this has a concentration. It's literally 1 cup per 2 quarts of Kool-Aid, right? Or in this case, it would be sugar water. So if it's 1 cup of sugar for every 2 quarts of water, this has a concentration of 1/2 cup per quart. When you do your division, or 0.5 cups per quart. So your concentration of this mixture is 1/2 cup per quart. So what happens if I add 2 more quarts? So add 2 more quarts of water, H2O. What happens to the concentration?
It decreases.
the concentration's the same.
I'm adding pure water to my sugar
The
water.
concentration decreases.
The concentration is going to decrease because the more liquid that's in there and the sugar is not changing, you're going to get less sugar per quart. So, how many quarts are in? I'm sorry, if I add 2 more quarts, how much liquid is going to be in this container? A gallon. So the measurement or the calculation is concentration 1, volume 1 is equal to concentration 2, volume 2. It's an inverse proportion because as one goes up, the other one goes down. If you added more sugar to the 2 quarts, your concentration of sugar would go up. So it has that inverse relationship. All right, so my first concentration is
A 1/2 cup.
a 1/2 cup per quart. So my concentration is 1/2. What's my volume of my first mixture? 2 quarts. So I'm just going to put 2 here. So this is cups per quart, and this next one is quarts. So C is measured in cups, V is measured in
What's that
quarts.
say on the bottom?
Cup per quart. Now be careful, C does not represent cups. C represents concentration. Concentration. All right, so this is going to equal, do I know the concentration after I added 2 more quarts of H2O? No. So I'll leave that as C, and if I want, C2. What's my volume after I add 2 more quarts?
A gallon.
Well, it's a gallon, but this is measured in quarts. This better be measured in quarts also. So, how do I find C2? Well, before you divide, I highly suggest you take these 2 numbers over here and put them together. What's a half of 2? 1. So this becomes 1 equals C24, or 4C2. How do you solve for C2?
Divide.
Divide both sides by 4. So your concentration is now 1/4 of what?
Sugar. Cup.
Cups
Cups of sugar.
per
quart.
quart.
Yeah.
This is a concentration, so it's a cups, in this case, per quart.
Wait, where you get the 4 part from again?
The 4?
Divide the 4.
When you're solving for this, 1/2 times 2 is 1. If I want to solve for C2, I got to get rid of the 4.
Oh, okay. So you don't use that 4 squared, or this just part
That's
of the
a C sub 2.
So it don't
That's
matter.
just a variable name.
Oh, okay.
If you want, you put X there. That'd be in chemistry, you're constantly changing the concentration of solutions because you want an experiment to come out a proper way. So you have to have the correct concentration mixed with the correct concentration. So having the right concentration is the trick. And I think this is the easiest way to do it. Now the 15 grams is the acidic salt that you add to water that creates an acid. And in this case, the acidic salt is 15 grams per milliliter. They also measure it as a percent of like hydrochloric solution and all that fun stuff. Hydrochloric acid, gotta love that stuff. So this is a concentration. Okay. Oh, by the way, we have an unlimited supply of this stuff. We have tanks full of this stuff. So however much we need out of it, we can get it. The chemist needs 345 gallons of a solution that has 10 grams per milliliter. Another concentration. All right. Now the cool thing is, he needs 345 gallons, but the measurements are in milliliters. And we do not have to convert gallons into milliliters. That's the beauty of these proportions. You don't have to do any of the conversions. You just have to make sure the measurements are exactly the same, top to, well, side to side in this case, instead of top to bottom. All right, so we're going to do C1, V1 equals C2, V2. And let's see if we can help the chemist get to his 345 gallons of 10 grams per milliliter solution. All right, so what goes in for C1? 15. So that's at 15 grams per milliliter. The volume for the first one?
345.
So we have 345 gallons of 15 grams per milliliter solution?
Oh.
Now, I have no clue. V. So we're looking for the volume necessary of the first one. Equals? Do I know the concentration of the second mixture?
No.
Yeah. 10, it's right here.
Oh, damn.
So this would be 10. Do I know the volume of the second one? 345 gallons. 345 gallons. So when we solve for V, what's its measurement units going to be? Gallons. The C's are measured in milligrams per milliliter. The V is measured in gallons. So when we solve for V, it'll be gallons. All right, so how do I solve for V?
You multiply.
Multiply these two together and you get 15V is equal to 3,450. And then divide both sides by
15.
15.
You get 230.
Oops, 15. So V is equal to 30?
230.
230. So it's 230 gallons. Yeah, I can't spell gallons. So 230 gallons of the 15 grams per milliliter solution will be exactly the same. The amount of stuff in it, it'll be exactly the same as having 345 gallons at 10 milliliters. Milligrams per milliliter.
I didn't know which one side is gallons. I I don't get
The first number, C1, is measured in milligrams per milliliter. V is measured in gallons, because this is gallons.
Okay.
Because once this is fixed as gallons, this is fixed as gallons. You can't change that. All right, so then the question becomes, how do I go from 230 gallons of the first solution to 345 gallons of the second solution? How would you do it?
Why would you substitute?
He needs 345 gallons.
Oh, you need that.
So far, he has siphoned off his little container 230 gallons of the 15 grams per milliliter.
Would you so you set up again, right?
Don't have to set up anything.
Add 115 gallons of water.
Add 115 gallons of water. What happens when you add water?
It dilutes
It dilutes the concentration down to what we want it to be. So all I have to do is take the 230, you take the 345, subtract the 230, and you get 115 gallons. So you're going to add 115 gallons of water. And what that'll do is it'll keep whatever the sugar, if you want to think of it, the same amount, but it'll increase the volume. But the concentration times the volume does not change. So the amount of salts in here stays exactly the same, the sugars, if you want to think of it that way. So by adding this 115 gallons, we have reduced the concentration down to 10 milligrams per milliliter. It's a neat little trick that you just have to add water. Just have to add water. So anytime you want to dilute something, like if you put too much salt in your soup and it tastes horrible, you have to add water. You can't do anything else. You have to just increase the volume of your soup.
I used to think you add sugar.
You counteract it with sugar? Yeah, I mean, you could, but still the salt is there. You really just want to add water. So if you're going to make a lot of mistakes in cooking, start off with a big 5-gallon jug, cook about 2 gallons of it, and if you screw up, just add water. And a few more things, you know, your potatoes and some carrots and all that fun stuff. And then whatever's left over, you just bring it to the soup. I don't know. Give it to somebody.
I have a question.
It tastes better now.
I have a question.
Go for it.
The stuff that we went over last week, where in the book can we
It's-
go home
It's on the syllabus where things are attached, but it's not directly.
and look? Well, I looked and I don't see nothing that even
There's
looks
only
like what
the
we went
appendix, but the appendix basically just has that chart on it. What was that? Add sugar. I know what I want to look at. All right. Enough cooking tips. Enough cooking tips. So, percents. By the way, we're going to be dealing with percents for the rest of the course in different ways and flavors and styles. So you have to get used to all the differences between percents, percent rates, proportion percents, percent increases and percent decreases. They're all treated a little bit differently. And then there's even the thing called points, and we'll talk about that a little bit. So percents literally means out of 100. Per being the out of. Cent as in century or cents. There's 100 of them. So out of 100. So if I have a fraction, we want to do a pure definition. A over B is equal to x out of 100 would be what percent of A over, what percent is A over B? Is basically what's being asked here. So by writing x over 100, this x, when you write it, is going to be written as x percent. So there's a correlation between how you work with percents and numbers and how to define a percent in one sentence, in mathematical expression. All right, so how do you work this? Well, let's look at like 4/5. Maybe a store is saying, oh, we're going to take 4/5 off your price. But 4/5 you don't understand, but the percents you do sometimes. Most people don't like fractions. So you go 4/5 equals x out of 100. Nice little proportion. Solve for x. So how do you solve for x? Cross multiply. I start with a variable, so x times 5 is 5x. 4 times 100 is
400.
400. Divide both sides by 5 and you get
80.
80. So when I write this 80, it's not 80 the number,
80%.
it's 80 the percent. So be really careful. 80% and 80 are two different things. 80 is a decimal value. 80% is out of 100. This also tells you how to change a percent into a decimal. You take x and divide by 100. So what's 80 divided by 100?
0.80.
0.80. So this is what's considered the decimal. And this, of course, is considered the percent. They are equal. 0.80 and 80% are the same value. Not the same number, they have the same value. So you got to get kind of clear on, are we answering in percent or are we answering using a decimal? Most people know this direction, changing a percent into a decimal. Very few know the other direction. And it's not that they don't understand to multiply by 100. You know, if you have 80.80, you multiply by 100 and you get 80%. It's that they forget when to do it. And that's the hard part. When do you change a decimal back into a percent? All right, what about this statement then? What if I have a over 20 is equal to 15 over 100? What am I asking?
What is the value of A?
Yeah, but what am I asking?
What is the percentage of
What's
A?
percentage?
What percent of
15.
15% of
A.
20 is
100.
A.
A.
So the 15 here represents 15%. The 20 is what you're taking it out of because it's out of the whole. 100 is a whole, so 20 must be the whole. So it's what percent? 15% of 20 is what? So the question here is 15% of 20 is A.
Out of 100.
Well, it's 15%, so that's out of 100. When you say 15% out of 100. So how do I solve for A? Cross multiply, you get 100A is equal to 300. So A is equal to 3. So if I do 15% of 20, the answer better be 3. Just a different way of looking at percents, by pure definition. So let's ask a couple silly questions. Ones that you should know how to do, but I always get nervous. Because when I assume something, bad things happen. 3 is 5% of what number? Now, we know what to do with this number. Percents are usually the easiest one to find. 3 is 5% of what number? When we set this up, it's going to be fraction equal to a fraction. The 5 obviously is going to be the 5 out of 100. So at least you get that part set up. Where people screw up is putting the A or the B in the correct spots. So is 3 the top of the fraction or is 3 the bottom of the fraction?
3 at the top.
3 is at the top because it's a fraction of the original number. So it would be 3 over,
B.
well, in this case, B or X. I try to use B myself. So how do I solve?
5B.
5B equals 300. Therefore, B is equal to 60. So 3 is 5% of 60. So if you did 5% of 60, the answer would be 3. Simple, right? Until you What number is 70% of 8? Highly suggest you concentrate first on the percent. Get that fraction out of the way and then concentrate on the second one. So it's 70 out of 100 to deal with the percent part. Do I know the part of the number, or do I know the whole of the number?
Part of it.
I know the whole. It says what number is 70% of the 8? So the 8 is the whole, and what we're looking for is the top, which is A. A is the part of B. And then, of course, cross multiply and all that fun stuff. So this becomes 100A is equal to 560, I think. I'm never good with my multiplication tables.
You're right.
Divide both sides by 100 and you get?
5.6.
So 5.6 is 70% of
8.
of 8. So another way of looking at this fraction is over of is equal to percent over 100. Is over of equals percent over 100. So if you look at the first one, 3 is, so he goes in the top. This one over here, of 8, he goes in the bottom, and the percent just goes where it goes. Do you usually see problems like this?
No.
No.
Only in math class.
Only in math class. But it gives you an option if you're looking for something. I'm going to give you lots of options. You get to decide which way you want to do it. A study found that 240 students at Central smoke, and 138 students
Drinks.
at North High School smoke. Can I answer this question?
No.
Why not?
You don't know how many students are in Central Ward.
I need to know how many students are in each of these schools, not just one of them. I need to know both. So let's say Central has 1050 and North has 595. Oh, by the way, when you watch the news, read a newspaper article and it has some numbers in it, there are some cases where they give you numbers, but they don't give you enough to interpret the results. They leave pieces out. They'll say 5%, but 5% by itself means absolutely nothing. All right, so can I find the percent of smokers at Central? What would you do? Well, it's X out of 100. That's the percent I'm looking for. What would be the other fraction?
240 over 1050.
240 over 1050. Now, whether you use a proportion or not, you still have to set up the fraction on the left to find percent. I don't care how you do it after this, but you still have to set up the 240 over 1050 to find the percent of students smoking. So here, if we cross multiply and all that fun stuff, we get 1050x is equal to 24000. Right?
Mm-hmm.
Divide both sides by
1050.
1050, so divide by 1050.
It's going to be a
22.9.
22.9.
yeah.
23%.
I needed that last word, percent. This is not 22.9 the number. It is 22.9% because x is always written as a percent. I'll try to leave x as the percent in all of my little formulas from here on out. All right, what about
I
North?
thought it would have been more than that.
You thought it'd be more than that?
Yep.
Why?
Oh, I don't know.
Oh, just looking at the numbers?
Oh, no, I was just talking about,
Oh, realistically?
yeah.
You think more than a third of the school smokes? Any high school?
Yep.
That's kind of scary. Wonder what the real statistic is. You know how expensive cigarettes are?
Yeah, $5 a pack. I don't smoke by now.
Yeah. I know. I buy them for those kids that can't buy them for themselves. That's why you know there's more than a third. All right, so to do the other one, it would be x out of 100. Obviously, this x will be for north itself.
It'd be 138 over 240.
138 out of 240.
Well, I thought 595.
Yeah, that was
138 over 595.
So who told me 240?
Oh yeah,
Yesterday, that was yesterday. That was essential. We in North.
Those are smokers to begin with. North is 595. I was going to say, wow, a lot of them are smokers.
Yeah.
So multiply and you get 595x is equal to 13800. And divide both sides by
595.
595. And you get x is equal to
23.2%.
2%.
23.2%. So the high schools basically smoke at the same rate. Awesome. Now, is there an easier way of doing this? Yes. If you haven't figured it out yet, do 240 divided by 1050 and hit equals. It gives you a decimal answer.
What is moving?
It's that to multiply by 100 and it'll change it to a percent. The danger is I have people that'll do the division and forget to change it to a percent and write that as the answer.
That's wrong.
So if you keep doing that, I highly suggest you stick with the proportion setup. It guarantees you multiply and divide by 100 correctly in the right situation. All right, so a little question added on to this. Can we say that 46.1% smoke at both?
No.
No.
Why can't we say that? Can't you just take percents and add them together?
No.
No. With percents, you have to be really careful. There's things that you can do with them, and there's things that you can't. That's one of them you can't. Why can't I?
Because it's different amount of students.
The different amount of students.
First.
This is only 595. This is 1050. Even if they were exactly the same, can you add the percents?
No.
No. A lot of cases, when you read like newspaper articles, they try to lean you into believing that you can, mistakenly, or they just don't understand percents themselves. So you have to be really, really cautious of your interpretation of percents.